This video will talk a little bit about life in the universe, and of course some of this is speculation, but we'll try to track down some of the science that would guide us in searching for life in the universe other than on Earth. And one strong place to look would be on planets that are around other stars. And this video will talk about that, and there'll also be a later video I'll make that will talk about this. I'll make some brief comments about evolution, the Bible, and intelligent design towards the end of this video. So, habitable zone. We have a strong leaning towards looking for planets that have liquid water, and sort of identify that as the habitable zone. So liquid water, that's 0 degrees Celsius to 100 degrees Celsius. We don't want it to be frozen. It's hard to imagine life thriving locked into the ice structure. And the cold temperatures also limit chemical reactions. They don't proceed as well at cool temperatures. Then on the high side, 100 degrees Celsius, we're getting into a realm where the activity, the energy in the boiling water disrupts cells, and you boil to sterilize things. That's killing off the germs that are there. So might be best to have it under 100 degrees Celsius, although I will comment there is life in the hot pools in Yellowstone National Park and so forth. There is life deep in the ocean near volcanic vents. So this is sort of ballpark numbers. So liquid water, that's something that we would like to have. Then there is an effect on the temperature of the planet due to natural greenhouse effect. This isn't man-made greenhouse effect, just an atmosphere provides a somewhat temperature buffer and an increase in temperature for planets. So the Earth is in the habitable zone around the sun, and we're getting to the place where we have to be a little concerned about being too warm. So habitable zone, basically, I'll use the criteria that we have liquid water as the habitable zone. So what about the stars where we might have life present on the planets around that star? So in terms of the scientific viewpoint of life, that life develops over billions of years. I'll have some other viewpoint on this lifetime later, but scientific view for life, billions of years. The star needs to be stable, so we're looking at main sequence stars. The other stages of a star's life, there's too much change on the luminosity of the star. Main sequence, we have a stable luminosity, fairly stable luminosity. We know that the lifetime of a star in the main sequence depends on the mass of the star. And when we have a 1.5 solar mass star, roughly it has 3 billion years of main sequence lifetime. The sun, roughly 10 billion years of main sequence lifetime. So from a scientific point of view, we would want to investigate stars that are 1.5 solar masses and smaller mass than that, because those stars have a long life on the main sequence, a stable luminosity where life on the planet could develop. There is a difficulty in getting too small for the mass of the star. If we have a smaller mass star, it turns out the region, the distance away from the star, where we'd have liquid water in the planet, it becomes narrow, more narrow than when we have a larger star. And there's a problem when we have this narrow habitable zone. It ends up being close to the star in a region where the gravity of the star causes tidal lock. Just as our moon always has one face towards the Earth due to this tidal lock effect, a low mass star would have a planet in its habitable zone tidally locked to the star. So one side of the planet would always be in sunlight, and the other side of the planet would always be dark. And there'd be extreme temperatures on the two sides. So that's not the best situation for life, probably. It's not impossible. Someone might live in the twilight zone between bright daylight and darkness, but probably we'll restrict our search to planets that have that have stars that are bigger than 0.5 times the mass of the sun. And then we're carbon-based life forms. There may be other forms of life that don't rely on carbon and organic molecules, but if we're starting our search with sort of what we know about, we know a carbon-based life form, so we'd like to have some carbon and other nutrients in the environment. So elements beyond hydrogen, helium, that means the population 1 stars. The population 2 stars are very low in abundance of the elements heavier than helium. So the population 1 stars, and those are located in the disk of our galaxy, so they've been enriched as supernovae explode and deliver the elements formed in the fusion process of the massive star, and in the supernova process, these elements enrich the gas clouds in the galaxy, and then the new stars form from those. So we might search for planets around stars about the mass of the sun in the disk of the galaxy. So just kind of giving the scientific viewpoint on where to conduct a search. Also, a single star is a little bit better for the orbit of the planet. If the planet is orbiting 2 stars, the orbit gets more complicated and can lead to the planet getting close to the stars or far away from the stars and not as stable, even being ejected from the star system. Though there are planets in orbits around double star systems, a single star leads to a little simpler orbit. We would like a circular orbit for the planet. If the orbit's elliptical, then the planet sometimes will be very close to the star, too hot, and the other portion of its orbit would be far away from the star and possibly too cold. So not the best for life. You like a more steady temperature. So here's a chart. You can do a little translation here. The orbit relative to the Earth's orbit. So 1 means this is the Earth's orbit, and we have the terrestrial planets, the Jovian planets laid out here. And then over here, the mass compared to the sun, so 1 solar mass. And there's this strip, the habitable zone strip, and I think it should be a little narrower down here, but that's okay. The situation here is for the more massive stars on the main sequence, they're more luminous, so the planet has to be further away to be in the habitable zone where liquid water would exist. The temperature between 0 and 100 degrees Celsius on this edge, 0 degrees Celsius on this edge. And then low mass stars have less luminosity, so the planet has to be closer to the star to have that correct temperature. Just to give you a little indication here what's happening to the habitable zone. We'll talk more about the Kepler spacecraft in a future video, but just want to let you know there are planets that are in habitable zones for their stars. These are confirmed planets in orbit around different stars that the Kepler satellite has identified. So Kepler, the 69 system in that catalog system, the Kepler 22 system, and you get an idea of the size compared to the size of the Earth. There's some other exoplanets that have been identified, just to give you an indication that these satellites now do have the capability for detecting planets even smaller than the Earth. Here's why we don't want an elliptical orbit, where we're too hot. Well, in this particular orbit it's liquid water, but too cold in the far extreme of the orbit. We'd rather have a circular orbit that stays in the habitable zone all the time. So what about some characteristics of life? Characteristics of life. Well, life is organized. You are organized. Your body has cells that play different roles, and you have metabolism. You take in food. There's waste products, but you use energy from that food. You grow after birth. You respond to stimulation. Your professor says, I'm going to give you a grade at the end of the semester, so you study faithfully. That's good. The life reproduces generation to generation. There's some variation that occurs. Our humans now are taller than they used to be several hundred years ago, and we adapt. An ice age comes along, and we find places to live to survive in the colder weather. Greenhouse effect comes along, and the Earth's temperature rises a lot, hopefully we'll have enough capability to adapt. And hopefully the temperature won't rise too much. We'll take good care of our environment. But I digress. So how about evolution and Genesis, science in the Bible? So the theory of evolution says that life started randomly from molecules forming and then cells forming and building up the life we see today. The Bible in Genesis would state that God created life, created the universe, and created life. Let's take a look side by side here. So the science theory, Big Bang, is how the universe begins. Genesis chapter 1, let there be light. As God created the universe, created space and time. Then the evolution goes along, cells form, life in the ocean forms, life moves on to land. In Genesis, the sort of period by period, day by day, but the Hebrew word for day can mean a period of time. So we get vegetation, trees, life on the land. We get water and birds and animals. And then evolution's brought us to the case of people in that theory. And the Bible has Adam and Eve, God creating humans, as the sort of wrap up to the formation here. Now, my personal belief is Genesis in the Bible does give a description of how God created the universe and created life and created us. We have the science theory, the Big Bang, universe of 13.77 billion years old or so. And I just would make you aware, in 2 Peter 3:8, a verse that relates to this timing, but do not overlook this one fact, beloved. With the Lord, one day is as 1,000 years, and 1,000 years is one day. God created time, and I believe God is patient, and I don't see a disagreement personally between the Big Bang and the version of Genesis of God creation. And I do believe that God created Adam and Eve, and it was not the random variations and evolution from some beginning. I won't go into all the other science behind that, but you should investigate this on your own. So write down some questions, ask your instructor, and for my students, and they know that I don't hold them to espouse my point of view on religion, so these comments on Genesis would not be on the test. So keep studying, ask questions.